Hi everyone, Christian Aprieso here to give you another tutorial on Nastran Solution 200. And here's what we are going to do in this tutorial. We have a very simple truss structure that you see here on the left. We're going to let Nastran automatically vary the dimensions. And our goal here is to minimize the weight as much as possible while at the same time satisfying our stress criteria. So by the end of the video, this is what you can expect to cover. I'm going to go over this example a little bit more in detail. And then after that, I'm going to formulate the optimization problem statement. This is probably the most critical thing to have before doing optimization. After that, I'm going to go through and walk you through each step that you need to use Nastran Solution 200. What files do you need? How do you configure your model for optimization? I will then perform the optimization with Nastran Solution 200, and then at the end we'll view the optimization results in the F06 file, Excel, and then I'll make a comment regarding the new optimized structural results. And then at the very end, we're going to update our original model with the optimized dimensions from our optimization. Before going any further, I'd like to point out that if you have any questions, comments regarding the video, I'm always open to the feedback. You can email me at this email address that you see here on the screen. In addition to this, if you want additional training, if you're a professional engineer in the industry and want more advanced training on Nastran Solution 200, I do provide this. If you are using something else besides Nastran, but you have a general structural optimization question, you can also contact me. And then if you want access to the Nastran Solution 200 web app, you can also reach me at this email, and I would be more than glad to work with you on that. And one thing I want to point out, this example is from the MSC Nastran Design Sensitivity and Optimizations User's Guide. This is in Chapter 8. The example is called the 3-bar truss example. This is actually a very popular example, so I wanted to start off the whole series with this particular model. I think this diagram does a very good job of explaining how this truss is set up. We have 4 nodes in total. Nodes 1, 2, and 3 are pinned. Node 4 is where we are applying our loading. And one thing to keep in mind with this model, there are 2 load cases or 2 subcases as you see here. Basically, we have 2 different forces for each subcase. One other thing I want to point out, here's the current stress state for this example. This is for load case 1. You can see that member 1 has a stress value of 13,000 psi. The second member has an axial stress of 4,000 psi, and the third element has a stress of, or axial stress of negative 9,000 psi. And so now let's go ahead and formulate our optimization problem statement. I'll go ahead and actually use this slide to discuss what our design variables, objective, and constraints are. So here on the left, you can see I have a summary regarding the design variables. Keep in mind that this model has various dimensions associated with it. It has a lot of material properties. These are all parameters, and we can select any of these parameters to be design variables. So for example, element 1 that you see me highlight here on the screen, we used a parameter A to define the area of that member. We did the same thing for member 2 and member 3. What we're doing with these 3 parameters, we're going to set these as design variables. So x1 will be the area of prod 11. So here what we're saying is take the parameter area and vary that throughout the optimization. We'll do that for the second and the third area. We also are supplying side constraints on the design variables. We are saying that the area can be no less than 0.1 and it can be no greater than 100. And one last detail regarding the design variables. We are saying that the area of area 3 should be equal to the area of area 1. So we are going to create what's called a variable length. Now, let's talk about our objective and our constraints. For the objective, what is our ultimate goal? What value are we trying to minimize or maximize? After you perform your simulation here, you're going to have a variety of quantities outputted. You're going to have things like displacements. You're going to have strain values for each element, stresses, and so on and so on. This is where you decide which output to set as the objective. It's very common to set the weight as the objective, so we are going to go ahead and set the weight as the objective in this case. As for design constraints, again, your model is going to be producing a lot of quantities. Here, for this scenario, we want to constrain the axial stress in P-rod 11, 12, and 13. So here what we are saying is take the axial stress for any element associated to P-rod 11, and it so happens that that would be this element. Do the same for any element associated with P-rod 12 and 13. So that would be this element and this element. Also, constrain the axial stress so it's within negative 15,000 and 20,000. And the second response or output we are constraining is the displacement. We are focused on node 4, and what we are saying is for the x and y components, make sure the displacement is no less than negative 0.2 and no greater than 0.2. So that's the optimization problem statement. You should always have this before ever performing an optimization of your own. And now here's exactly what I will cover. Like I said at the beginning of the video, I will go through each step in detail on how to perform Nastran Solution 200. So I'll describe your starting point. I want to make sure you have all the necessary files before getting started. I'll then go ahead and walk you through the steps of converting your BDF file to Solution 200. This is where we are going to define our variables, our objective, and constraints from the optimization problem statement. I will then actually perform the optimization with Nastran, and then towards the end, I'll view the optimization results. I'll also show you the new axial stress states in the members. And then at the very end, we're going to update our original model with the latest parameters for areas. These would be the optimized areas. One thing you'll see me use throughout this tutorial is the Nastran Solution 200 web app. This web app will let you take one of your BDF files and convert it to Solution 200. You can define your variables, your objective, your constraints. You would then export that to a new BDF file. You would then run that in Nastran to perform your optimization. And I'll go step by step in a moment. If you want access to this web app, my email is on every slide. Feel free to pause the video, send me an email requesting access to the web app, and I would definitely work with you. So let's go ahead and get started. Here, let me minimize my windows and show you Patran. You could be using some other pre-post processor. The first file you want to have, here I have Patran loaded with the model. You could be using some other pre-post processor. The most important file to start off with is your BDF or DAT file. This BDF file was created by your pre-post processor. It's essentially a description of your entire model. What materials are you using? What's the loading like? Where is every node located? What elements are you using? This BDF is what we are going to take and convert to Nastran Solution 200. So with that, let's go ahead and get started with the procedure. One thing you will definitely need is access to the Nastran Solution 200 web app. Again, if you want access, you can reach me at this email that you see me highlight here on the screen, and I would definitely get back to you. So this all starts off with step 1. We want to go ahead and select this BDF file and load it to the web app. The web app will go ahead and identify all the parameters that you can set as design variables. So if you want to set the Young's modulus, the Poisson ratio, the density, or the areas, you can do that in the web app. Here, I want to set the 3 areas as design variables. Notice as I select the plus icon, it moves the parameter to the next table. Here is a list of all my variables, which I would then have to go ahead and create the lower and upper bound for this. And so let me go back to the PowerPoint and look at what my side constraints are for the design variables. So here I see it's a 0.1 and 100. So let's go ahead and type in 0.1 here and 100 here. One thing to keep or put attention to is the web app will automatically create your Nastran bulk data entries. So the DV Pro entry, the DESVAR entry, traditionally you would probably have to either type these out or use some other application to do this. But in the web app, as you make your design variables or any other objective or constraints, the web app does a lot of the work for you. So there we are. We're done configuring the 3 design variables, x1 and x2 and x3 for the 3 areas. Now we have to create the variable length. Remember that we said that design variable 3 should be equal to design variable 1, or the area of element 3 should be equal to the area of element 1. So here what we can simply do is take the label, we'll type in x3 here, and type in x1 here, and there we go. The web app has to automatically create our D-link entry with this relationship. Now let's go ahead and continue on to the objective. Here it's very simple, just select weight here, and then you can leave the defaults here. Let's move on to constraints, and now focus on configuring our stress and displacement constraint. Remember that your model is going to output a lot of quantities. This is your opportunity to single out specific quantities to constrain during your optimization. So here, I want to set the stress as a constraint. And next thing I want to do is change the property type to PROD11. These elements will have either axial stress or torsional stresses. And here I want to focus on just the axial stresses, and I want to apply these constraints to any elements associated with PROD 11, 12, and 13. And then for the lower and upper limits, I'll type in 15,000 or negative 15,000 and positive 20,000 here. And here on the right again, you have the web app automatically output the entries for you. The next thing we want to do is define a displacement constraint. So for this, filter through the table. You can go page by page, or you can just type in letters there and it'll filter for you. So I'll go ahead and select on displacement one time, and I have a new row here at the bottom. The corresponding label is R2. Here I want to focus on the X and the Y component, and let me zoom in just so you get a better look at that. So here I can select the T1 or X component. I can set the T2 or Y component. There's also an option called 1-2 for the X and Y components. So I'll select that. I'll scroll a little to the right. And here we're applying this constraint to node or grid 4. And then my bounds, if I look back at the problem statement, let's go ahead and take a look at that. I believe the value is negative 0.2 and 0.2. So we'll type in negative 0.2 there and positive 0.2 here on the right. One last thing we have to do is create a constraint group. Remember that there are two load cases in this model. So what we have to do is click on add constraint group, and we'll go ahead and take R1 and R2 and we'll type those in here, R1, R2. And then for the subcase column, we'll go ahead and apply this to all the subcases. So what we're saying is we want to apply the axial stress constraint and the displacement constraint to both 1 and 2 load cases, or all subcases in this case. After you're done here, you can go to the exporter, and here you'll notice that what was once a solution 101 BDF file. So this is our original BDF file, and in line 4 it says sol 101. The web app has configured this to perform solution 200 or optimization. This file is completely new, so you'll have to download this version. The file on the right that defines all the design variables, the objective, and the constraints, you also have to download this file. Now let me go ahead and minimize all of these windows and create a new directory on the desktop called one optimization directory. This is where we are going to perform our actual optimization. So I'll move this directory to the right, and then here on the left I will go to my downloads folder where my new BDF is. So let's go ahead and move those files to the right. So now I can perform the optimization with these two new BDF files in Nastran. And let me go ahead and select the model BDF file. And the next thing I want to do is walk you through how to interpret the optimization results in the F06 file. You obviously want to make sure that the weight has been minimized, your variables have changed during the optimization. I'll show you how to do that in the F06 file and Excel, and I'll go ahead and walk you through the process of viewing the new structural results. So let me go ahead and minimize this. It looks like our optimization has finished. Let's go ahead and open up the F06 file and scroll to the very bottom of this file. What we want to look for is this table, summary of design cycle history. After that, you want to check this message, run terminated due to hard convergence at an optimum cycle number. This is the number one indicator telling you that the optimization went through successfully. Once you see this message, you can then review the rest of your results. If you have any other message, I definitely recommend you double check your work. So here, let's look at some of this data. A lot of this data might be intimidating when you first look at it, but it's surprisingly easy to interpret. This column that you see here is the actual value of your objective. This first value in this column is the original or initial mass or weight of your truss. Here the optimizer has gone through what looks like 7 design cycles, and on the final design cycle where it reached an optimum, you see that the new weight is reported as 2.69. This next table is indicating the changes in your design variables throughout the optimization. So at the very beginning, we started with cross-sectional areas of 1, 2, and 1. And then at the very end, we have these new areas of 0.8, 0.3, and 0.8. Just in case you want to look at these in graph form, you can use Excel to look at the same information. And I'll walk you through that right now. One thing I should mention, this BDF file and another Excel template is located in the video description. Feel free to download those files if you want to follow along. In the video description, there is a link to an Excel template, and let's suppose I just downloaded this and you see it on my desktop. Drag that Excel template to your optimization working directory. This is where you've performed your optimization. There is a CSV file. This CSV file is reporting the same information from the F06 file. The objective is reported here in row 10. Information regarding the design variables are reported in row 17 through 21 here. What you can do with the template when it's in the same directory, you can double or open the template, enable the content so you have macros enabled, and then click on the button that says create optimization plots. The template will go ahead and create the plots for you. So here you have a plot for the objective or the weight of the structure throughout the optimization. You have information regarding the design variables here. One thing I'll point out about this plot, you notice it looks like design variable 1 is missing. Remember that we said the area of element 3 should be equal to the area of element 1. So what's happening here is X3 is actually overlapping the plot for X1. So that's why it looks like X1 isn't plotted here. It actually is. It's just because X3 is plotted on top of it. So that's how you look at your results in graph form. Again, the template, there's a link in the video description below if you want to follow along. And the last thing I want to leave you off with is how to view your new structural results in your pre-post processor. Here, again, are the new files that have been created during the optimization. Here, this OP2 file, yours might be XDB, it might be MasterDBAll or some other result type. This result file has the new structural results for your optimized model. So what we can do now is attach these new results to your pre-post processor. Again, you might have an XDB, a MasterDBAll, or a OP2 new file. And what I'll do is attach this OP2 file to my session here. And when you look at the results, you notice that we have 4 results. The reason we have 2 results is as follows. 2 of these results are for the very initial original model. Remember, we had 2 subcases. One good indicator to tell you that this is the initial design, if you look here, at the very end there are these markers, D0 and D7. D0 is indicating these are the structural results from the initial design. D7 is indicating these are the results from the design cycle 7, which is a very design cycle in this optimization attempt. So these are the optimized structural results. What I can do then is view the results here. So maybe I'll take time to go ahead and do that just to show you what the before and after is. So just bear with me while I do this. And here you can see let me fix the number or the notation for this here. So here, this element was initially at a stress state of 13,000 psi, or rather the actual stress was 13 psi, and so on and so on. If we then look at the new optimized structural results, we'll find that the new axial stress is 20,000 psi. Here it's 13,000 psi, and here it's negative 7,000 psi. One thing I want to note about these new structural results, again, the optimizer will vary the parameters, your design variables. It will continue to do this until the objective has converged, or if you've hit one of your constraints. Here, the optimizer has gone from 13,000 psi, and it went all the way until one of the members touched the ceiling in the design constraint bound. So here it hit 20,000 psi, which is the upper bound for the axial stress constraint. The other ones are still within the limits, so those are satisfactory. And I figure I wanted to point this out just so you think later on that there could potentially be one of your design constraints that's have the ceiling touched. So the last thing I want to do is update the very original BDF file with the new dimensions for the areas. If I minimize my desktop and we look at the very first directory that we started off with at the very beginning, this BDF file, again, this BDF file is linked in the video description if you want to follow along. This BDF file has old areas configured inside of it. So here on my desktop, I'm creating a new directory called updated model. I'll paste a copy of this old original model here. I will open it and show you the old areas. So if we look at PROD 11, 12, and 13, we see the old areas are listed here. If we go to the optimization working directory, there is a PCH file that's been created, or a punch file. I'll move the BDF file to the right. And if we look inside of the punch file here on the left, we see new PROD entries for 11, 12, and 13. you notice that the areas are actually different. They are 0.8, 0.3, and 0.8. These are the new areas from the optimizer. So what we can do is simply take these PROD entries, take the old ones here on the right, and just replace them. And then after we do that, the new areas are in the file on the right. We can save it. And now if we look back in that folder, this PDF file has been updated with the new structural dimensions from the optimization. So that was essentially the last thing I wanted to leave you off with. Again, we went through an entire procedure for Nastran. We went and started off with the file that's been produced by your pre-built processor. So we started off with the BDF file. I walked you through the process of using the web app to create your variables, your objective, and your constraints. We saw the results in Excel. I showed you the new structural results. And then at the very end, we updated our original model. So with that, I want to give you a big thank you for watching. As always, if you're a professional engineer in the industry, if you want training so you can perform optimization on your own, if you have a question, if you want access to the web app, you're more than welcome to contact me at this email address, and I would definitely get back to you. Thank you for watching.